Okay, yes, hello and a very warm welcome to ARADEX. My name is Julie Hemming-Barreis. I'm from the sales department and I'm here today to take you through the function of safe TorqueOff in mobile inverters. So, safe TorqueOff in mobile inverters. This is something that most people have heard of, but no one really seems to know what it is. This is what we will be showing you today. We've divided this EFACT seminar into 5 chapters. The first chapter, we want to give you a brief introduction to the basic function of an inverter with a connected electric motor. And here we have a diagram, the schematic diagram. So by using 3 controlled phases, the inverter creates the desired rotational frequency and the required voltages and currents. By using 3 internal transistor pairs, the voltage of each phase can be switched to DC plus or DC minus, but nothing in between. And to create the required voltage for each phase and each time, the inverter, for example, can switch 80% of the time to DC plus and 20% to DC minus to create a voltage of 80%. And this is what we call PWM, pulse width modulation. And the modulation frequency must be much higher than the rotational frequency, and the inductance of the motor works as an averager. And here we have the scheme of the inverter. Each power transistor is switched by a driver board, and the driver boards receive their commands from the drive controller. The driver boards are grouped in the 3 top boards to switch the top transistors and the 3 bottom for the bottom transistors. And we'll see later on why the driver boards are grouped this way. To create a rotating field, the 3 phases need a phase shift between each other. In chapter 2, we'll have a short look at the safe TorqueOff function in industrial production machines. In industrial production machines, safe TorqueOff has been around for a long time, according to the DIN norm, as you can see here. It's known to switch off the low voltage power supply of the driver boards in a safe and redundant way. This works very well in production machines. However, if we use an electric motor with a field weakening function, solving the safe TorqueOff function is more complex. How do we want to go about that? So we now want to have a short look at the behavior of electric motors with field weakening functions for uses in traction applications. Here we show the characteristics of a PM motor, permanent magnet motor, without field weakening, the FW. Classic permanent magnet motors provide a torque nearly independent of the speed. Only close to maximum speed do we see a small reduction in the available torque. According to this behavior, the power increases nearly linear with the speed. And for propulsion and some other applications, e-motors with a so-called field weakening possibility are more suitable. And this field weakening has to be accomplished by the inverter and must fit exactly to the technical data of the motor. From 0 speed to nominal speed, the torque is independent of the speed and the power increases in a linear fashion. From nominal to maximum speed, the power can be nearly constant and the torque decreases correspondingly. This kind of power spreading creates big advantages, especially in propulsion applications. And as a second effect, the current required by the inverter to create the set torque at low speed is reduced by factor 2 or 3, requiring a smaller inverter. And above nominal speed, the field weakening function has to be applied. And this again is accomplished by the inverter. As a result, the phase voltage of the motor is kept below the planned voltage. This is shown on the lower horizontal green line, which is given by the high voltage supply voltage, for example, from the battery. But if the inverter is not working, for example, going into idle mode, the generated voltage of the motor at higher speeds exceeds the planned operating voltage and even exceeds the critical voltage level, the upper horizontal red line, given by the regulations and/or the technical limitations of the product. So now we want to take a look at how to avoid this overvoltage situation for a permanent magnet motor running at high speed in the event of a safe torque-off function of the inverter. And we'll compare permanent magnet motors and AC induction motors. Short circuit as a feasible solution. A motor design with so-called buried magnets, as shown here, is feasible for good results in the field weakening area in normal operation. And the second advantage is the unwanted break torque is very low in the event of an all-phase short circuit. This behavior strongly depends on the motor design, and you have to take it into account when you're designing the safety features of the application. For example, in a traction application, to avoid dangerous behavior of the vehicle. This example is a truck with a 90 km/h maximum speed, and it's taken from an actual real ARADEX traction project. And it shows the unwanted brake torque, the lower red curve, compared with a normal torque, the upper blue curve. The speed is shown as correlated speed of the vehicle. And we can see here, a relevant brake torque will only be seen at very low speed. Here, the peak is at 2.7 km/h, which is completely uncritical for this fully loaded truck. And even at this very low speed, the torque is below 25% of the normal peak torque of the motor. And at higher speed, it's still only a few percent. Yeah. So the conclusion for permanent magnet motors with buried magnets, the short circuit on all phases is a feasible way to avoid overvoltage at the higher speed mode. For permanent magnet motors with surface-mounted magnets and without real field weakening, the short circuit on all phases should be avoided because of unwanted brake torque. In this case, idle mode is best. And for AC induction motors, the idle mode is in case of error or in the event of safe torque-off is a must, because in this case, the first time slot after running at full power and then changing to a short circuit, the flux of the rotor will cause extremely high peak values for the short circuit current and unwanted brake torque. And in the last chapter, we want to show how we implemented the safe torque-off function in Model 3 series of our VECTOPOWER inverters. So here we're showing the single inverters and the double inverters, the two models we have available. Our single inverters, the upper ones, cover a range of continuous power from 30 kilowatts up to 180 kilowatts and supply a three-phase connection to the motor. And the double inverter supplies six phases to connect the motor to avoid thicker cables. And this supplies 300 kilowatts of continuous power. Besides the modes idle and short circuit, which I've already mentioned in the case of an error, or if the safe torque-off function is needed, the VECTOPOWER Model 3 offers a third mode, and this is the conditioned short circuit. And this can be a real advantage in your application. And so, what is this? Conditioned short circuit, the reaction after starting safe torque-off. The inverter is idle for a few microseconds and then measures the DC voltage. It creates a short circuit if the generated DC voltage is shifted higher than the level that has been parameterized. And the short circuit can be reset by an external command. Here we have the schematics of the Model 3. Part 1 of the safe torque-off function, no rotating field can be generated. And this is implemented by switching off the top drivers in a safe fashion. Part 2 of safe torque-off, we avoid the overvoltage problem from PM motors by using the 3 bottom transistors. And in this way, the VECTOPOWER Model 3 and the safe torque-off can be used with all kinds of motor topologies. PM, permanent magnet motors with surface-mounted magnets, with buried magnets and field weakening, AC induction motors, and also the pure reluctance motors, which we haven't explained here. So, thank you very much for your listening in, for your attention. Please don't hesitate to contact us at sales@ARADEX. Challenge us with your application. Give us a problem to solve. We like challenges. We'd love to hear from you. Thank you very much and goodbye.